Today we start the second part of our course, and we're leaving behind the pseudo relational databases discussion and going into MapReduce, which is essentially the fundamental technology that that big data is all about. So we'll spend some time on this, and I hope that we will have some fun with it. Let's move on. So, excuse me. MapReduce is not new. MapReduce used to be a part of programming languages from way back when. Lisp, which was a programming language in the 60s, had map and reduce, and it did what this slide shows, which is you map a square, the function square, to a list of 1, 2, 3, 4, and it gives you 1, 4, 9, 16. And then if you say reduce with the function plus, it'll actually add them. So, the basic concept has been around forever. It's easy to see that this is something that is very easy to distribute because you can take one of the parameters and give it to one processor, and take the second parameter and give it to a second processor, and so on. And so you can get a lot of parallelism by just expressing everything in terms of vectors, which is what map and reduce do. The thing that is new here is that we've started doing now is failure and retry semantics, and by that we mean you can take a large computation and spread it across literally hundreds and possibly thousands of low-end servers, and by low-end we mean just your commodity hardware. And if you can do that, it'll run all of those tasks in parallel and give you results in a timely fashion. What could be simpler, right? So here's slightly broader picture of what happens. You've got a whole bunch of data sets here, and it may be these little disks might be one, might be some keys and values, and there might be others, and we distribute them across a whole bunch of machines, and we specify a map function, which takes these keys and these values and produces a different set of keys and values. And that's all it does. And it's a function that you, as a programmer, have to write. Then there's a shuffle step, which is implicit. And what it does is it takes, for example, if we had 3 keys that were output by the map function, it combines all of those keys and gives us an array of all of the values associated with that key. And the reduce function is also a function that you write. And the system basically takes care of everything else. So we'll talk about that in just a minute. So here's a picture of exactly the same thing that we just talked about, where you have a large file, and you give that file to a mapper, and this line represents the mapper, and the mapper produces some keys, and in this case it produces blue, green, and yellow keys. And then there's this intermediate shuffle step, which basically says take all the blues, put them in one place, take all the greens, put them in another place, and the yellows, and then have the reducer do what got specified in the reduce, and we get our results. I mean, it's pretty simple. What we will discover in the next few slides, and actually in the next few lectures, is how this formulation actually helps us do a number of very interesting computations in a general kind of way. So let's go there. So the first example that everybody uses for MapReduce is word count. You're given a whole bunch of files, and you are expected to count the words in that file. So in this example, I have 5 files, and they're separate. They're essentially separate books, and the job is to figure out how many times each word occurs. And so we see A occurring 29,000 times, and the occurring 45,000 times, 46,000 really, and so on. So well, this is fine. It's not very interesting, but we'll get to the interesting part in a minute. But let's just stay with this and talk about how MapReduce does the work. Well, what we do is the map function reads all of those files and finds the unique words. And for each word, it produces the word itself followed by 1. And that's all it does. It's a very simple computation. And then the reducer takes the word, and it takes the count that it has received. We just a moment ago said that the count is going to be 1. And it basically emits the word followed by the sum of all the values that it received. So, and then it basically saves the results into a table, and then we can go and look it up. So let's go into this a little bit. Well, actually, let's do a second example. This is a crawler, so it's a web crawler. It goes and finds content of all the web pages in the world, and it comes back with pairs of this is the URL and this is the content. And from that, we are supposed to find the reverse index. So let's imagine that all of the URLs we were talking about were works of Shakespeare, and as we then look at what kind of result we want to see that Ariel shows up in the Tempest at offset 105. Ariel also shows up in the Tempest at a different offset, and so on. The word lady occurs in lots of different places. So it shows up in Othello, it shows up in Hamlet, and so on. And of course, every time the word lady occurs in Othello, it'll have the same URL but a different offset. So we'll get lots of entries. So okay, that's fine. That's still not very interesting, but let's just, we can at least imagine that if we then used this table as the input to a search engine, as soon as somebody typed in the word lady, we could come back and say, that word occurs in these files at all these different locations. Okay, so how do we do that? We do that by saying we're going to map the document name and the content. And for each word in the content, we're going to basically emit the word and the URL and the offset. So notice the URL and the offset are here, and the word itself is here, and that's what the mapper is going to produce. And the reducer then will take each of those keys, and the values will be a list of these URL offset pairs, and we are going to just emit that. And as a result, we can now produce this table, and this table helps us look at helps us figure out where a particular word occurs. And this example, we just took works of Shakespeare, but there's nothing that really limits us to that. So it's a nice couple of examples that we'll work with. Let's keep going and find that there are some implementation questions that we haven't really thought about. When we said, if I go back here, when we said here's a map reduce formulation, we're going to take a whole bunch of keys and values and process them to produce another set of keys and values. We just acknowledge the fact that we can do this in parallel because each one of these things is independent. We never really said whether the level of parallelism is one machine or one process or a million processes or anything in between. Similarly with the reduce function, we just said is we're going to get keys and we are going to get values that all need to be reduced together. But then we didn't say anything more about that. So the question of how many processors we should use is an open question, and it's really not something that the algorithm itself, the MapReduce algorithm, will decide for you. You end up having to specify that. And same thing with reduce. We don't know how many processors we should use. We don't know what the right algorithm is for saying which words should go to which reducer. That's a different decision that we have to make. But bottom line is that the algorithm that we write, namely this, doesn't care whether things are distributed 4 ways or 1 way or a million ways. It all works exactly the same way. And so the decision of how many processors and how to allocate them and all that depend on the problem. It depends on the hardware we have available and so on and so forth. But the algorithm itself doesn't care. Okay. So what are we doing? We are basically taking all of the keys and values and we're splitting them into m chunks, and we run a map task on each chunk, and then we basically shuffle the output and partition the output into a whole bunch of regions. And then we basically, after all the map tasks have completed, we run a reduce task on each of the regions. That's really what we've talked about. And there's this question sitting here saying, why do I need to wait before all the map tasks are done before we can start running the reducers? Why can't we accelerate things a little bit by starting reducers right away? Well, and the answer is you can't, because for one thing, the reduce, one map task at the very end can introduce a new reduce key. So you end up having to wait anyway. And the second thing, which we will deal with in more detail pretty soon, is that the reduce operation is not commutative necessarily. All of those values that we got in this example where we said the reducer just sums the values, summing needs is a commutative operation, but other functions that you write, which basically operate on an array, may or may not be commutative, and so you can't assume that that reduce will continue to work. So you end up having to say we need all of those inputs before we can start the next step. And the last reason for waiting is that reduce can't finish anyway, right? Because while maps are going on, so we've got to basically there's not much we can do until all the maps are done, and then all the reduces are done. So we might as well wait to allocate resources to the reduce jobs. So in the beginning we'll have a whole bunch of processors running mappers, and then when all of the mapping is done, then we can run the reduce jobs. Okay. The other thing that I mentioned when we started this was that the key to this new MapReduce, beyond what we've known for a long time, is the fact that we can do fault tolerance. And that's really important, especially if you've got 1,000 processors or 10,000 processors, because the more machines you have, the more likely that at least one of them will end up failing in some way. So the concept of things failing along the way is kind of baked into the design of this. So if we detect through a heartbeat as to whether a set of machines is working or not working, and if we find something is not working, we need to basically redo all of the map tasks, and then we need to re-execute all of the reduce tasks. And so it basically means that the map tasks as well as the reduce tasks may end up running more than once because we tried it and then something broke, and then and if something broke, we don't know whether it broke before the failure or after the failure and all that. So we end up retrying some of those jobs, kind of at random. So we need to be aware of that. And what that means is, let's do the second bullet first, and then we can go back to the main point here, is that the operations we specify for map and reduce must be idempotent. And that basically means, idempotent is a big fancy word. It basically means that I can run a task multiple times and it will not have any effect on the result. So, the implication is that if I had a map task that sent emails to users, I can't afford to repeat that task multiple times. Users get upset when they get 3 copies of the same email. And even worse, the second case here, which is, if we have to reduce a user's account balance, we better be sure that we're doing it only once, right? So the rule basically is that map and reduce have to be written in such a way that they can be tried again, and without any loss of generality or without any loss of function. What all kinds of tasks can we do here? I mean, we can do analysis tasks. We had the example of a reverse index. We had the example of a word count, but those are all analysis tasks. We can pretty much do anything that is parallelizable. If the task can be parallelized, we can give it to a MapReduce problem, and we can configure it as a MapReduce problem and use a MapReduce framework for solving it. That still leaves out a whole bunch of problems that we can't solve this way, but it's a very good start. So now next few slides, we're going to be talking about refinements. We've set out the basic idea, and now we are trying to just focus in a little bit and see what happens and see what kinds of optimizations become necessary in having this framework work for us. So one thing that happens sometimes is you gave the tasks to 100 different machines, each one working on a separate piece of data, and there are some slow workers which take a lot longer than all the rest of them. It could be because there's some job running on that machine. Maybe it's going through a massive garbage collection. Maybe there's a bad disk on that server. Maybe there's some configuration problem. So towards the end, what we have to deal with is that that 95% or 90, pick your favorite number, of the jobs are done, but there are a few laggers. And what's been found to be very useful is near the end of the phase, we just spawn backup tasks for things that haven't finished yet. And we give it to a different processor that was working on something else prior. And because the computation is idempotent, we can afford to assign this task to another processor and know that it'll work, that it won't conflict with the first one, and whichever finishes first wins, and we just go kill the next job. So this is an improvement, a refinement that has been found to be very useful when setting up a big infrastructure like this and using it for MapReduce. Another refinement is, you've all seen this. Some inputs, some functions work well, and you test them, and then when you give them some real data, then all of a sudden they fail. Well, maybe there's a non-ASCII character in one of the inputs. Maybe there's some bad data in some other form, and so the thing that worked, when you were testing this code, doesn't work when you run it with all of the data, and so dealing with data specific issues. What we end up doing with that is when there's a data specific issue, something takes a long time, we stop it, we run it on a different machine, which is what we talked about on the last slide. And if that doesn't work, we just kill the record and we keep going. That's actually a configuration parameter. If you want to make sure that all the records get processed, you can set it to be, if any record fails, just fail the entire job. But quite often you don't want to do that. So So there's an escape clause here. So that's basically the operation of a MapReduce framework. The framework itself is very simple, and it runs because it can literally spread out the computation to hundreds, if not thousands, of machines and let them do their thing and let them come back with a result, and we handle failures. So now we're going to just have a little bit of a talk about how we got to MapReduce, what all has happened, and where these systems are at the present moment. So the first impetus for this was the Google file system, paper that was published in 2003. And I've included the reference here, and this yellow link shows you where the actual paper is, and a few excerpts from the paper itself. The main thing that they were focusing on was it's a distributed, scalable file system, and it delivers very high aggregate performance to a large number of clients, and it's built using commodity hardware. The second thing they talk about as one of the design goals, and one that they talk about as having met, it basically said this is the way to store large amounts of data. And in 2003, they were storing hundreds of terabytes, and across literally over 1,000 machines, and being accessed by hundreds of clients. So at that point, by 2003, they were already using this system pretty widely within Google. And then they talk about some extensions that they had to do to the file system, because your generic file system, and they were using Unix, doesn't support the kinds of operations that they were trying to do. So we'll talk about a little bit of that in the next few slides. The second paper that, notice the first one was in 2003, the second one was in 2004, which talked about MapReduce. And you can read the summary, but basically that's what I've summarized in the first 10 or so slides of this presentation. And they talk about how many real-world tasks are expressible in this model. Not all, but many. They make a big deal out of the fact that they're using commodity hardware, and then they talk about how they use it for search engines and so on. And you can look at that paper from 2004. The thing that happened after the two paper that I just cited, it created a lot of buzz, as you would expect, and that's when Hadoop was born. So some people took the ideas presented in the Google papers, which, by the way, were not open source. They were just papers that talked about the concepts that they were using, and so the effort to basically implement something akin to MapReduce framework was started at Yahoo, and soon it became an open source project under Apache, which is where it still lives. So it was implemented in Java, and so that's how it started. So notice that there's 2 years between the original paper on MapReduce and Hadoop, which was the first open source implementation of the MapReduce concepts. So what is Hadoop? Well, Hadoop is an open source implementation of the MapReduce concepts. There are three major providers: Cloudera, Hortonworks, and MapR. They're slightly different in their goals. They each provide their own own version of Hadoop, and you can install it either from Cloudera or Hortonworks and so on. Since then, a number of other companies have made this platform available on their cloud services, and Amazon's Elastic MapReduce is one. Google's Cloud Dataproc is another, and just to be clear, those are not the only ones. There's Microsoft, IBM, Oracle, so a whole bunch of companies will provide all of this software pre-installed, and so all you need to do is connect with them and start using it. And it takes a while to actually set a particular version up, which is why I've shied away from trying to build it within WPI, although we could. To go a little bit more into the details of Hadoop, because now we're getting specific about it. And so what exactly does Hadoop do? Not just the general programming constructs, but how do we make it work? So here's the first architecture picture of Hadoop. There's two major components. One is this distributed file system, which is kind of exactly what the 2003 paper talked about. So HDFS is an implementation of the concepts that were described in the 2003 paper. And MapReduce, the MapReduce engine is an implementation of the concepts that were described in the 2004 paper. So what's the overall concept? Put my glasses on. So what happens, the way it gets configured is there's a top-level tracker which is responsible for, receiving your requests and then handing them out to a number of servers. And on the same server, typically, there's and although it could be different, there's a name node which keeps track of the file system. So the dark blue is where the computation happens, and this light blue is where the data lives. And it all lives on the same machine. Computation and data are very close to each other. So that's the controller, and then we have these data nodes which carry a segment of the data, and then they do all of the computation on that data. And this I've shown two, but this can be literally thousands. You'll notice that this idea is very similar to what we saw in BigQuery as well as with Redshift. Namely, there's a controller, and then there's a whole bunch of machines that carry a segment of the data. So that's a pattern that we will see repeating itself many places in this world. So going a little bit more into HDFS. HDFS, hardware failure is the norm rather than the exception. So they keep multiple copies, and each HDFS machine keeps only a part of the file systems of the data. And we'll talk in just a moment about how they're organized. And the last piece is detection of faults and quick automatic recovery is a key architectural goal. So there's machines, there's servers we don't talk about here, or tasks, whose job it is to make sure that everything is running smoothly. And if a server is is not functioning, to replace it with something that is functioning, and do all of the necessary reporting on recovery of that. Go ahead and take a look at the design, but this is really what this is really the main points. These are the main points I want you to get out from this paper, this slide. A second thing, which I talked about very briefly a few minutes ago, which was there were changes needed to Unix to basically be able to run to be able to access the data, the HDFS data, quickly. So what do I mean by streaming data access? So streaming access really refers to, and I want to be careful here because we use the word several times in this course. I can think of at least 3 different uses of the word. So just be careful when we say streaming. We have to be clear on which version of streaming we're talking about. The streaming that we're talking about here is just being able to read file from disk. So what happens is, in a normal file system, what's important is that you'll be able to go to any part of the file and be able to read it, immediately. And so, so there's a lot of design and coding that is done for being able to, to orient the disk the right way, to be able to position it where it is, and then be able to read it. Less important in this case. What is more important here is that we want to just position the reading head on the disk, and then we want to read just a long stream. And we want to keep things double buffered, which means there are 2 buffers in memory, one that's being filled from disk, a second one that is being processed, and then as soon as the one that's being processed and the one that's being filled have been exhausted, we just flip them and keep going. So a lot of emphasis on being able to read them, read the data continuously without having to reposition the read heads on the disk. So that's the emphasis. It's all about high throughput of data access. And so for supporting that, they had to actually make quite a few changes into Unix so they could read at the kind of speed they needed to. The third thing is that the typical data set is very large. So a normal Unix file system, I think it breaks up a file in I could be wrong on this, but I think it's like 64 kilobytes. These partitions are not 64 kilobytes; they are several megabytes. And so again, the idea is that you are reading these files in large chunks and processing them. And so a number of fundamental changes at the Unix level. So the next thing that we should note is typically HDFS files are written once and then they are just read multiple times. So it's not a file modification kind of regime. It's an environment where we typically read from a file that's been created and read it multiple times, but not much by way of of updates. And even in the latest version of Hadoop, they talk about there's a plan to support appending rights to files in the future. So this is something that's been, the desire has been there, but there hasn't been a strong enough need to go implement it right away. And last but not least, or second last, the idea is we want to move computations to the data rather than moving data to the computations. We talked about this as a principle, like during our first lecture. But the idea is that your data is distributed, and if you can avoid having to load all of that data into one place, you win. And any strategy that says you're gonna load the data to your application, that's not gonna win you, because then you get into scaling issues. This is kind of a minor one, but still quite important, which is, if I have 1,000 processors, if you have to upgrade the OS on 1,000 processors, you're not going to do it all at once. So at any one time, your configuration will have things that have different OS versions, maybe different processor speeds, and all of that. So the underlying hardware is heterogeneous, and there's no getting out of that. So I'm going to go back to, so that's the basic message of how Hadoop in general, but HDFS specifically, which is what we've been talking about here, are configured and built. So now we go a little bit more into detail. Same picture. So the execution of Hadoop is coordinated by one master node and n slave nodes. So I show two here, but that's n. I think we should. I'll let you read the words on this slide, because I want to go talk about how the data itself is organized. And here's a decent picture of how the data is organized. So there's a name node which has all of the mapping structures. The data itself is, so here's one rack, here's another rack. Rack being, basically a panel into which we have multiple disks plugged in. And notice how if a client is writing a data block, it may need to write to two different places, and so then some nodes here, some blocks could be copied from one rack, one position to another. And so there's built-in redundancy. We never keep just one copy of any block. But the way these blocks are configured, they're spread out among those machines, and so that if we suddenly lose one of these machines, we haven't lost any of the data. So this one might have a copy here, this one may have a copy here, etc. So it's not that one disk is a copy of another disk, but the design makes sure that each block is copied somewhere else. And that's what a node really looks like. So each of these things you see is one machine, and all of these machines together form a rack. And here's another rack. And that's what if you want to know what a node really looks like, this is what the hardware in a room looks like. So the job tracker, which is the thing that runs on the name node. So here's another piece of terminology which may have gone by. Here we go. So the job tracker runs on the name node, and there's only one copy of those. There's a task tracker which runs on this machine for this node, on this machine for this node, and there's n copies of the task tracker. So the name node decides how many mappers we're going to have and where the mapper is going to run. The file itself will be replicated. In fact, here we show that block 1 lives on node 1 and node 3. Block 2, or maybe there's a third one someplace. No, I don't see it. And block 2 lives on node 1, node 2, and node 4. And block 3 lives on node 5 and node 7. And so they're kind of spread all over the place. And what the name node is going to do when it comes to running a mapper is, if it's going to be dealing with some data in block 1, it will prefer to run it either on node 1, because block 1 is here, or if it can't do that, it might run it on node 3, because that piece of the data also lives there. And so the task of allocating where I should be running a map job is not arbitrary. It depends on how the data is mapped. And so that's something that we need to be aware of, although it's hidden pretty well in the implementation, so we don't need to be super aware of it. And the task tracker is the piece that runs on each data node, and and as it makes progress, it reports the results back to the name node. So in this picture that we saw, maybe 20 slides ago, we see that there are 10 mappers here, and there are 3 reducers. So we will eventually need to run 13 different jobs, and they will likely run on there's many options, but there'll be a name node and probably 10 mappers will be and 10 task nodes, and then once the map tasks have gotten completed, then 3 of those 10 will get used for running the reducers, and that's what the overall configuration might look like. Okay. Here's some exercise that I would like you to do, at least to get started. This is just for play for now, but don't be surprised if it shows up on a test. So the assignment is Gutenberg.org has all these books, and those books are actually available in many different formats. So what I'd like you to do is go to the UTF-8 version of those 5 books. They're all by Lewis Carroll, and download those books and then upload them to S3 or Google's cloud storage and run word count on them. And if you can do that or do some part of it, I think we will be that much further ahead. That's it for this lecture. We got much more to go, but